Hello, and welcome to today's ACM SIGSOFT webinar. This webcast is part of ACM SIGSOFT's commitment to provide value to its current and future members. The ACM SIGSOFT webinar series features speakers from the Future of Software Engineering track at the International Conference of Software Engineering, as well as select keynote speakers and distinguished paper authors. I am Robert Dyer, Assistant Professor at Bowling Green State University and member of the SIGSOFT Executive Committee, and it is my pleasure to welcome you today. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you're experiencing problems with the slides or audio, press the F5 key in Windows, Command R on a Mac, or refresh your browser on mobile devices. Or you can close and relaunch the presentation. To control volume, adjust the master volume on your computer. If you have questions during this webinar, please type them into the Q&A box at any time during the webinar and click the Submit button. At the end of the presentation, we will have time to respond to the questions. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. Today's presentation is Basic Data Analysis Techniques, Part 2 of 4 in the series on Fundamentals of Measurement and Data Analysis for Software Engineers by J Frailey. Dennis is a retired principal fellow from Raytheon, where he worked on software metrics and safety-critical applications. He also served for over 40 years as an adjunct professor of computer science at Southern Methodist University, the University of Texas at Austin, and the University of Texas at Arlington. Dennis is an ACM Fellow and an IEEE Senior Member. He was the 2008 recipient of the ACM Lifetime Achievement Award in Computer Science Education and the 2013 recipient of the IEEE Computer Society's CSEET Nancy Mead Award for contributions in support of software engineering education. Dennis, without further ado, take it away.
Okay. Before I begin, I want to mention, if you look at your bottom resource list down there, you'll notice Part 1 feedback. I responded to questions we didn't have time to answer during Part 1, as well as a few other pieces of information that might be of interest. I plan to put a similar feedback file up there after today's webinar, so in a few days you may notice a Part 2 feedback up there. Okay, let's move on. We are now in Part 2 of 4. Last time we talked about measurement. Today we are going to continue to talk about measurement, but also move on into analysis. The focus of today is in two areas. One of them is in talking about the international standard for metrics processes for software and systems engineering. This is a standard that is very important to follow and pay attention to when you are setting up a metrics program, and it talks about the whole big picture, and we'll be covering that. We'll also be talking quite a lot about statistical distributions, which are one of the most important things to know about your data before you apply statistical techniques. In Part 3, we will then dive into specific statistical techniques and how they can or cannot be used for specific software type situations. And in Part 4, we'll be talking about robust statistics and other methods that don't necessarily that work well when you don't have data that's well behaved and therefore cannot apply the conventional statistical techniques. So what we'll cover today are four topics, the two important ones being the measurement process there and the statistical distributions, but we'll also talk about a few other things. I want to remind you that a lot of this material is based on this textbook, which has a lot more background information if you're interested, and I will refer to that book from time to time. Okay, let's talk about problems with measuring software. One of the most important things to keep in mind about software is that it doesn't have to follow the laws of physics. which means there are a lot of things you can assume when you're designing a piece of hardware that you cannot assume when you're designing software. For example, with hardware, you can calculate the amount of energy going into the device and then maximize how hot it can get. You can't do that sort of thing with software. And therefore, one of the things I encountered a lot in industry is hardware measurement techniques that didn't apply to software simply because the hardware techniques were based on the laws of physics. An example is you can increase input by a very tiny amount and increase the output by a gigantic amount in software, but that's rarely possible in hardware. And you see all this all the time in things like video games, where things that are physically impossible to do are represented there in the video game. Another issue with software is that an awful lot of what you produce when you produce software is not code. One of the mistakes I see made quite often is that software developers will focus on whether the code is correct and neglect to pay attention to these other things. And the problem with that is that software doesn't have a static kind of a substance. You modify software, you change it, you upgrade it, you maintain it, you repair it, and you need all these other things to be correct in order to do all those things correctly. I used to teach a course in this subject, and I had students who were in a maintenance organization, and they talked all the time about how difficult it was to do maintenance when the specifications were wrong or the documentation was wrong or the code didn't match the design and they didn't know quite where the problem was. If you only measure the code, you don't really understand your software. Okay. Now, I threw one of these out last time, and I'll throw it out now. This is just an exercise. Come up with examples of how an error in something other than code that could cause your software to fail. It's a good little exercise to think about. Okay, now I want to cover 4 fundamental failures in software engineering measurement, and this is directly out of the Fenton textbook. The first one that Fenton mentions is that we have requirements that we cannot measure, or at least we don't have a very good way to measure. Here is some typical software requirements: user-friendly, maintainable, and so forth. These are typically not quantified, and if they're not quantified, then it's not possible to measure them. And so how do you know whether you've satisfied the requirements? How do you know whether your product is user-friendly? And that, of course, directly relates to testing. How do you know whether you have properly tested it to see if it's reliable, for example? And not only do you not know how to do it, but you can get into conflict with your customer over exactly whether it's reliable enough or powerful enough or whatever it might be. The second failure that Fenton points out is that we often don't measure what we do. These are the typical sorts of things we do when developing software. And as Fenton points out, we often don't quantify what we do in these areas. How many of us know in some quantitative way how much time we spent in requirements, much less how good a job we did when we wrote our requirements, or whatever other activities we might have participated in. And as a result, we don't fully understand where our costs are. We can't really, in a quantitative way, evaluate how well or how poorly we are doing these various things, or even whether doing too much or too little. And so when we're trying to make improvements, we don't necessarily know very well where to make improvements. The third failure that Fenton points out is that we don't have a good way to quantify quality. These are some typical quality attributes. And how many of these do we know how to measure? How do I measure portability? How do I measure supportability? Well, there are ways you could measure these things, but one of the things I teach in one of my courses is how most of the ways we measure these things are not very good. In particular, with reliability, a lot of the well-known measures aren't very applicable to software. A lot of work has been done in reliability in a hardware arena, but a lot of that doesn't really work for software. And as a consequence of this problem, we run into all kinds of problems with knowing whether our product has quality. We don't know how to predict what it's going to cost to support it. So we often sacrifice quality in order to meet deadlines or cost goals. And part of the reason is we don't really have a good way to quantify quality. Okay, Fenton's fourth software failure is that we tend to use things without having really given them a good scientific assessment. In other words, we base our decisions on hype rather than facts. Here are some typical claims. I pulled these off of a couple of websites just for this webinar. Claims about agile development. Those are some of the claims. Claims about open source software. Claims about object-oriented programming. Very few of these are based on any genuine scientific assessment. Very few of them are really quantitative. How do you quantify how well engaged your stockholders or stakeholders are? Claims like these are based on promotional hype, opinion, not scientific studies. They're anecdotal, and as a consequence of this, we tend to select things based on what's popular rather than what we really know in a quantitative way to be effective. Sometimes we spend a lot of money to learn techniques and tools that may not actually help us all that much. And another way to put it is we're not being scientific, we're not even being engineers about it. We're not engineering our software, even though we call ourselves software engineers. We are using something because we heard several people say it's a good way to do things. Okay, so I wanted to go over those because they illustrate the kinds of problems we have when we try to use measurement with software. Okay, now we're going to talk about the measurement process. The measurement process is the process by which we measure, but it's more than that. We do three things. We establish a measurement program in our organization. We implement that program, and then we evaluate the consequences or the results and decide whether we need to make changes. Most organizations don't do this in a very methodical way. The ones I have seen tend to be ad hoc. For example, I witnessed an organization where the boss said, I just want you to come up with 20 measurements. And the employee said, well, what do you want us to measure? He says, I don't care. The more measurements we have, the more we'll impress the higher level managers. And that's not a good basis for deciding what to measure. And another thing I've seen happen is, as a matter of fact, I was hired as a consultant one time with a company that had an incredible amount of data but had never done any analysis on the data. And therefore, they didn't really know what they had. Now, to improve this situation, an international standard has been established as a model for how you ought to go about these things. It's IEEE ISO standard 15939. It's a very good standard to pay attention to if you're going to establish a measurement program because they've given a lot of thought to the things that you want to do if you're going to be successful. It defines what are the characteristics of a measurement process. For software development and systems engineering, interestingly enough, they concluded that they needed pretty much the same concepts for both. The standard does not define a process. It defines a set of criteria for a good process. So you can assess what you're doing and say, are we doing it well? The standard says what a measurement process should be like, what its purpose should be, what its outcomes should be, and it also describes a lot of associated activities. The idea is you define your measurement process, and then you look at this standard and say, are we satisfying all the things that this says we should do? It also defines an information model and some associated terminology. And it covers all the activities that are listed there. Notice that it includes the analysis and the determining whether the results of the analysis are valid, which of course is one of the things this webinar series is all about. The standard can be used by suppliers and acquirers. For example, if you have a subcontractor, you can use this standard to assess how well your supplier is measuring things. Okay, this is a big picture of the model. And we're going to go over some of the pieces of this picture, but I wanted to give you the big picture first. The part there in the middle that has a blue background is what's called the core process. And we'll be focusing on that because that's the part where you spend most of your time. But let's look at the far left. The first thing you have to do is get commitment. That means people have to be willing to pay for, to provide the resources for, and to support the measurement process. That may involve paying for a measurement database. You'll notice on the bottom there's a database that plays a rather core role here. Being willing to pay for and maintain that database. It means hiring people to do the analysis, hiring people or developing equipment or whatever to collect data, and so forth. Then once you have established a commitment, then for any given particular project or whatever, you plan what you're going to do, and then you do it. That's these two middle parts here. And then you evaluate the consequences and say, do we need to make changes? For example, improvements of some sort. As an ongoing activity, the measurement process provides information to the people who are leading the project, managing the project, and the software developers themselves. This information tells them things that are going on, and that means they know how to make improvements or they know what's happening. You'll also notice this blue line that says information needs. This is where you start when you're planning your process. You say, what do I need to know? And that's an important part of deciding what to measure. Now let's look at the core process in a little more detail. And you'll notice that 3 of the 4 boxes have to do with performing, 1 has to do with planning. And you'll also notice the role of risk management here, because that's one of the main reasons you use measurement for, so that you can manage risks. Okay, let's look at planning. You define what your information needs are. What do you need to know? And part of that is usually driven by whatever your goals are for your project. We want to get it done by a certain deadline, or we want to achieve a certain performance level or whatever. And then once you know what your goals are, then you select what to measure. Now, I could have 2 or 3 webinars on the subject of selecting what to measure. I refer you to the work of Vic Basile, and there's a reference list at the end of this webinar material that gives you some references to some of his more recent work. Then you plan the data collection, analysis, and reporting procedures. In other words, you give some thought to how are we going to collect this data, how are we going to analyze it, how are we going to report it out. And that really requires a certain amount of work. I used to teach a course when I was at Raytheon on measurement, and one of the things we did is we had student exercises, and our very first exercises presented the students with a bunch of data and asked them to do some basic analysis. And what we were wanting them to determine is that this was bad data. It had not been collected properly. And that's one of the very first steps in data collection, is making sure that you have good data. what are your criteria for evaluating the results and evaluating the metrics? Once you have done those things, then you can understand the magnitude of what you need to do, so you have to get approval to spend those resources, and then you have to deploy whatever technologies are needed to do it. Then you move into the collect phase, where on a regular basis you collect data. And one of the important steps here is to integrate that process with the process of developing software. In other words, you don't make data collection something outside the process. You make it a natural part of the daily work of people. This may require some work very closely with the software developers, for example. Communicate the process, deploy the process, collect the data, and store it. That's the collection process, and there's a lot involved there. Once you've collected data, then first thing you need to do before you analyze it is to refine it. And we'll talk a little bit about that later. But basically that means doing things like simple calculations, getting rid of duplicates, sorting things. Sometimes you collect more data than you need, and you need to pull out just the part that you need, things like that. Then you analyze the data, report the results, and I want to emphasize the difference between analyzing and reporting. Too often in the business world, I've seen people take raw data and report it to the management, and everybody draws totally inappropriate conclusions because they haven't done good analysis. And doing analysis in a meeting is not the way to go. You want to do good analysis and then present the results of that analysis or discuss the analysis before you report it. All right, finally, you utilize the metrics. Well, you may change your project. For example, you discover you're doing something too slowly, or something isn't being very effective, or whatever. That's a very important step here. Then the next thing you think about is, do we need to change our process? Are we going about things inappropriately? Is our method of defining or documenting requirements not working very well? Is our peer review process ineffective? We're wasting our time. We're not doing it properly. Then once you've done that, you need to move on, and for some reason it won't go. There we go. Change the measurement process. By that I mean you want to change the procedures you use for measurement if you conclude by your analysis that you aren't collecting the data properly, or you need to change the definitions of something or whatever. A very common problem is that different people interpret things differently, and therefore you need to sometimes clarify all that. I have to apologize. I'm recovering from a cold. Okay. I want to make one little point there. The part about changing the measurement process is not technically part of the core process, so for what it's worth. Now, when you measure something, it's important to decide what are you measuring and why are you measuring it. So you need to have an objective, so people know why you are collecting this. If you collect data from people and they don't know why you're collecting it, they are motivated. They are not motivated to make sure they give you the right data. It's a common psychological problem. If people know why you are asking for the data, they're much more likely to be cooperative in giving you good data. Okay. The interpretation must be clear. In other words, you have to give some thought to how are we going to interpret this graph or this data, or when we show this to management, what is the implication of this line being above that line, or whatever it might turn out to be. And finally, it must be something that the customer of the measurement wants. Now, who is the customer of the measurement? Well, it's often the manager. But is it something they actually want? If it's not, then it's a waste of time. One technique for doing that is to think of 3 elements for the objective of anything you're measuring. What are you trying to accomplish? In other words, what do we want to do? And you use words such as the ones shown there: evaluate, control, predict, report, whatever. And then what is it that you are hoping to actually report on? In other words, what attribute are you trying to report? And we're trying to talk about the speed of something, or the schedule of something, or the performance of something. What is it that you are trying to measure, and what attribute of that thing are you trying to measure? And ultimately, why are you doing it? What is your purpose? Why am I going to do this? What is my purpose? Here's an example. I want to estimate the warranty cost of the new operating system in order to prepare a support budget. Now, that's a very reasonable purpose. And you'll notice that I've color-coded the words. The estimate is what I want to do. The warranty cost of the new operating system is the attribute of an entity. And the prepare a support budget is the purpose. Okay? Now, you must communicate all this to people so that they understand why you're collecting the data. One of the mistakes a lot of people make in measurement is they collect data and they don't tell people why they're collecting it. And when you collect data without telling people why, they get suspicious, they don't cooperate, they give you bad data, they don't try hard to make sure they give you good data, and so forth. And if you go to an organization that's an effective user of metrics, you'll notice they have graphs everywhere. They have charts everywhere because they're demonstrating their use of the metrics so that people are cooperative. Okay, now you have some data. Well, let's talk about the term metrics. One of the terms defined by that standard I mentioned, the ISO standard, is a base measure. A base measure is a factual quantity that you can measure, as compared with a derived measure, which is something you compute, usually using base metrics. And the idea is that the term metrics can mean either of those, but in the international standard terminology, you distinguish between those two things, and you also distinguish other terms, because you want to make sure that you know exactly what the terms mean. Measurement experts will talk in terms of base measures or derived measures, not in terms of metrics, because they want to be absolutely clear on what they're specifically talking about. And here's a little diagram that illustrates the relationship. There's something you're measuring, such as a software development process in action or a piece of software as it performs and you're testing it or something. The base measures are factual things that you can measure: how fast something is, how many of something are going on. The derived measures are calculated based on usually the base measures, and they provide information to satisfy an information need. So here's a little example. You're measuring things like how many units you produce or how many people there are. That's called the head count. How many lines of code there are, how much money you've spent. Those are base measures. And then the computed measures are the units per month, lines of code per staff month, things of that nature. And the reason you compute those things is to satisfy an information need, which in this case is how productive are we. So that's the kind of relationship between all those concepts. An information need is an insight desired so we can understand something. Here's some examples. Productivity is an insight. We want to know how efficient we are. Cycle time is another kind of information need. It says how fast are we? How quick are we? Another one is cost. how much is it costing us to produce this thing? How many people are we paying for how many hours, how many machines, etc.? Now, an information need is usually expressed as a question, and that's an important thing to keep in mind for the following reason. I mentioned the work by Vic Basile. He is very famous for something known as the goal question metric paradigm, which is the idea that you figure out what your questions are, and then you come up with things you can measure to answer those questions. Well, in the ISO standard, they talk about something called an information need, and the information need in the ISO standard is the same thing as the questions in the Vic Basile model. So that's why I emphasize that information needs are usually questions you want the answers to. And often there are many different ways to measure something, and the information need might be the same, but the way you measure it might be different. And so part of what you have to do is to say, what can I measure, and will that satisfy my information need? Okay, now once we have some data and we know what information we want, what do we do with it? Here's an example. Some people are doing something to do with when to play golf or something, and that's a bunch of data. It's called a data set. What these data are they are measures of attributes of entities. I've used those terms before, and I'm going to explain what we mean in a moment. What kinds of things do we want to know? What are our information needs typically? We want to know characteristics of things. We want to know relationships between things. We want to know which method is faster. How many defects are there? Does this work? Those are the kinds of things we want to know. And the first step is to organize the data for analysis. So I mentioned refining the data, eliminating duplicates, computing totals, things like that. Sometimes it involves more sophisticated things, which we won't have time to discuss here, such as data compression, figuring out how to reduce the data, or there's a whole bunch of techniques called data reduction, where you extract the most important information from the data. That's called refinement. Once we've done the refinement, then we can compute the derived measures that we have decided are the things we really want to know, like lines of code per month or whatever it might be. Now, the idea is that the derived measures are based on information needs. They're things we can compute in order to answer our questions, to provide the information we need. Whereas the base measures are the things we can actually measure by looking at the thing that we are analyzing. Now, let's talk about analysis. One option is to simply look at the data. Here's an example of an organization that's looking at how many sales they make in each continent. And there's only 5 data points, and you can just look at the numbers and pretty much figure out what's going on. Sometimes you have to do something a little more complicated. For example, here's an example where you've decided you need to sort the data. This is BBC looking at different programs they have and trying to figure out how many people watch each program. And they decided it's easier to do it because they have so many programs that they sort them. And the simple process of sorting them makes it possible to do all the analysis you need to do in this example. Another option is to graph things. This example is how the poor, the middle class, and the rich spend their money. And it doesn't take more than this graph to pretty much figure out what that graph is telling you. And you can create that graph by just creating a graph from the raw data. So those are some of the simple methods, but it's not always that simple. Here are some examples of data that you might have collected where the relationships and the things you're interested in are a lot harder to see. And this is the sort of situation where statistical methods are often helpful. And that leads to our final topic today, which is statistical distributions. Now, statistical techniques are often used to help us describe attributes and relationships. We can determine high and low, we can compute averages, we can compute mathematical relationships like if you double this, what is the effect on that? And of course, last time we talked about the importance of making sure you have the right scales before you can do some of these things. We can also determine patterns. These are all things we can do with statistics. And one of the most important things we have to look at before we use statistics is the distribution of the data. So to explain that concept, suppose you had 30 software developers in your programming team, and you had evaluated them in terms of ability, and you divided them into 5 categories, ranging from very poor to very good, and you knew what percentage of your programmers were in each category. Now, this is called a distribution. You have accounted for everyone, and you have numbers associated with each of the different options. So consequently, this is called a distribution. It simply explains how many there are in each category, and they are in order. Notice you have to have an ordinal scale. This is a graph of that same data, programming ability, and what percentage of the people are in each category. And you can look at that graph and tell pretty much what the data are telling you. Now, suppose I picked a random developer from that group of 30, and I wanted to know what is the probability that they will have any particular level of skill. Well, I can determine that from that distribution. And in this case here, I've replaced the percentages with decimal numbers, but they're really telling you the same thing. And when you do it with probabilities like this, it's called a probability distribution. Now, in order for it to be a valid probability distribution, you have to assign a probability to each of the possibilities, and they must be numbers between 0 and 1, and they have to add up to 1. So it's the likelihood that a randomly chosen value from the collection will have a given result or outcome. Now, suppose I wanted to know if a randomly chosen developer will be at least average. Well, in that case, I could get this thing to work. There we are. There's our chart. Well, these last 3 are average or better. And with the nice thing about probabilities is we can just add them up. We can add the probabilities for each of those 3 and add them together and say the probability of being at least average is 0.7. And that is one of the simple uses of a distribution. Now, in passing, I want to make an observation that there's something called a uniform distribution where all the options are equally likely, and the graph is pretty boring. But nevertheless, technically, it's a probability distribution. Now, here's where things get interesting. Suppose we have a lot of options. Suppose we had a large organization with 200 programmers, and they ranged in age from 18 to 72, and we wanted to understand something about our future pension costs or something. So we decided we were going to make a distribution of all the people. There are 55 possible values, and I don't have room on the slide to show them all, so I've just shown the youngest ones here. But you'll notice that when there are a lot of possible values, the probabilities start to get really tiny. And so that's an important point. We'd have a long list with very tiny probabilities. This might be a little more difficult to analyze. Not quite so obvious. Here's what it looks like if you draw a graph. And it looks like a pretty noisy graph, and I'm not sure it's all that easy to understand what you're seeing out of that. Here's a bar graph of the same data, and that's not any more useful either. What if it was an infinite number of possibilities, or at least a really large number. Like, for example, if you were looking at the sizes of your software, and you were looking at how many lines of code do we have in each of our software products, and they had a huge range of possible values, and as a consequence, it wouldn't really make sense to take each possible value and give it a probability. The probabilities would be really tiny. So there are two ways to deal with this. One is called discretization. The other one is called use of a continuous function. We're going to say a lot more about these in the third webinar, but I'm going to say some about them today. In discretization, what you do is you take your list of 55 in this example, and you break it down into categories. So in this case, I've broken it down into the 7 categories that you see here. And you'll notice that the probabilities are now larger and more sensible. You only have 7 of them now. And this is what the graph looks like. Now, this is a lot more sensible graph in terms of being able to interpret something out of it than the ones I showed a few slides back. And the reason is that by discretizing things, we have kind of eliminated the clutter and put in just the facts, so to speak. Now, this is a very good example of how discretization can really be beneficial. Discretization tells us things we didn't see before. This is a line graph of the same data. And you'll notice that it sort of has the shape of the top of the bar graph. And this might be another way to look at it. But this suggests another concept. What if there were a mathematical function that produced that curve? Well, if there were, then we could look at that mathematical function. Well, this is known as a continuous function approach. When there's an infinite number of possibilities or a very large number, very often you can do a continuous function. Now, this is an example where the function doesn't match the data that closely, but it's at least in the same general shape. And you'll notice the bar graph represents the actual data, it may be discretized, and the the curve is a mathematical function that sort of represents that. Well, in order for this curve to be a function that represents a distribution, the area under the curve has to be equal to 1. It's the sum of all the probabilities, and each of the infinitely small points on that curve is a probability of a particular value. Now, the advantages of doing this is that we have statistical and mathematical techniques we can apply to these functions. The drawbacks is, one of the drawbacks is that you have to find the function. I didn't put that on the slide, but another one is that you can't conclude data about individual values because they're infinitely small. You have to conclude things about ranges. But that's okay. Now, let's look at what is probably the most well-known distribution curve called the normal distribution, sometimes known as the bell curve. And the idea of the bell curve is that it represents a situation that occurs a lot in nature. Here's how a bell curve might be fitted to some actual data, for example. I pulled this off the internet. This is something to do with flying and signals and navigation signals helping a pilot fly an airplane. And I don't know what it means, but you'll notice there's a red line and a blue line, and they both sort of have the same shape as the normal distribution. And in fact, when they do the theory behind this, they use the normal distribution to figure things out. So the idea is that we can reach conclusions about the data that we might not have been able to reach had we not seen the mathematical function. And this is a very common distribution, as I've said. Here we have a diagram of height of people, U.S. People, men and women men on the left, women on the right. The men come a little closer to fitting the normal distribution than women, but the point is that you might be able to draw some conclusions about the height of people using calculations based on the normal distribution. Many statistical concepts are easy to explain using the normal distribution. We'll be getting into that a little bit in part 3. Now, before we wrap up for today's webinar, I want to talk just a little bit about, for those of you who have some mathematical background, the normal distribution is a type of Gaussian distribution. Here are some examples of some Gaussian distributions, and you'll notice one of them is the normal one, the red one. A Gaussian distribution is a subset of an even larger set called elliptical distributions, and those are some examples of elliptical, and you'll notice again the red one is a normal distribution. So for those of you with a mathematical bent, that's a little bit of background. And one of the reasons I showed that is that sometimes you find that a normal distribution doesn't fit your data, but one of the other distributions does. And here's some examples of some of the most well-known distributions that statisticians have come up with. And you'll notice that they're various shapes, and you may find that your data fits one of these shapes. So a lot of the times what you do is you look at the shape of your distribution and see which shape it seems to be simple or it seems to match. Maybe use a curve fitting technique. A lot of people with statistical backgrounds spend a lot of their time figuring out what distribution curve fits my data so that I can do analysis of the data. One very common distribution in many situations is the chi-squared distribution, which kind of looks a little bit like a normal distribution that's kind of tilted in one direction. That's the reason that's because the chi-squared distribution cannot go below 0. So it's what's called a tied distribution. And I apologize for the fact that this symbol didn't show up. We thought it was correct. We've had trouble getting certain mathematical symbols to show up here, and apparently I overlooked this one. Okay, that's the end of what we're going to talk about today. I did want to mention some reference material here, including the 2 books by Basili. And that's the end of today's part. Next time, in part 3, we'll take all the basic material we learned today and start applying some specific statistical analysis techniques to that data. So that's the end of today, and we're now open for questions.
Thank you very much, Dennis. So our first question is essentially asking, for a employer who perhaps is not currently doing any kind of data measurement on their software, are there any kind of good rules of thumb on things that they should measure?
Good rules of thumbs on things that they should measure. Well, my seat of the pants response is that you have to start by figuring out what you want to know. What are your goals? What are your information needs? And that can vary depending on your organization. It's very common for managers to want to know things like how fast are we, what is our productivity, things of that nature. And there are various things you can measure there. And I'll have to say that in my feedback file that I will create and post in a few days, I will try to give you some very specific examples. The problem I have with an off-the-cuff response is that it depends so much on what the organization's trying to accomplish that it's hard to just say you should always measure this. I would rather say it's probably more important to figure out what is it that we really need to know, what information could enable us to do something useful.
Okay, thank you. So do you have any guidelines on practices for essentially collecting data and helping to ensure the quality of that collected data?
Well, you have to begin by defining the data very clearly. What do we mean when we say, for example, we want to collect how many hours people worked? Well, you have to be very clear on that. You have to say, do we count overtime? What do we do about breaks? What do we do about times that, is there a difference between the way we count paid overtime and unpaid overtime? You have to be very precise about what you mean. And one of the other things that happens there is that if you're measuring different projects, you may find that different projects interpret things differently. So it's often a good idea to get the various people involved and say, this is exactly what we mean, and make sure not only that they understand what you mean, but that they are willing to collect the data the way you have defined it. Because one of the problems you can run into is if different people collect different data because they thought it meant something different, then you can't draw any good conclusions. A really good example of this, I was reading in the newspaper not too long ago, where at the federal government level in the U.S., they collect data on domestic violence, and they collect it from every state. And every state collects it from every municipality. The problem is every state defines it differently. So what counts as domestic violence in one state doesn't count as domestic violence in another state. So when they try to aggregate the data at the federal level, you can't make a good assessment of the situation, because it appears that there's more domestic violence in this state than in that state, but it may have more to do with the way they've defined what domestic violence means rather than the actual facts. And so getting your data straight is really important. And a related thing is making sure that you have a clean collection process, making sure that people are motivated to give you good data, and that you have a way of figuring out right away when you've collected bad data. Now, that's some general types of answers, and I'll try to give a little more information in the information I'll provide later.
What kind of data elements do you think could be collected to help predict software defects, other than the defect type or the phase?
Well, I think one of the most important things to keep track of is where the defect came from. In other words, where did we make the mistake that led to this defect? For example, was it a poorly stated requirement? Was it a design mistake? Was it a coding error? Was it a misinterpretation of something? And the reason you want to know that is so that you can pin down the ultimate cause of the problem. If you're making a lot of requirements errors and you fix them during testing and integration, you don't stop new requirements errors from entering into your flow. But if you say, these mistakes are due to making a bad requirement, then you may focus your attention on improving requirements, and that may help stem the flow of those defects that are the result of requirements mistakes.
So when we talk about metrics, sometimes there's a human element involved. And so when you talked about one of your examples where you were measuring a discrete distribution and you had the examples very poor to very good, if that's applied to people and it could possibly affect their job or salary, what is a good way to actually measure that kind of a metric?
Well, again, I may be able to give a more thorough response in the written material that I'm going to prepare here. But my immediate thought is you need to focus on the process you are following, not on the people who are doing it. And you need to say, if, for example, let's suppose a lot of people are making programming mistakes. You don't want to just say this person's a bad programmer. You might want to say, why are they making this mistake? What is the reason why this mistake is happening so often? Did the person get poorly trained? was an example that I'm very familiar with was we had an excellent programmer who was doing software for a nuclear power plant, and he made all kinds of mistakes because he didn't know anything about nuclear power. He was an excellent programmer, but not a physicist. And the problem was that the physicists were specifying requirements in terminology that made sense to physicists but didn't make sense to a programmer. And so the programmer was making assumptions about what those requirements meant. And when he would ask the physicist, well, can you explain what this means? The physicist's attitude tended to be, anybody ought to know that, whereas, in fact, not anybody ought to know that. And so one of the problems was simply not having paid attention to what is it about the way we do our job that is causing this programmer to make this mistake, as opposed to blaming the programmer. And you have to kind of take that attitude whenever you're measuring something that involves people. One of the best ways to do that is to work with the people and say, what could we measure that would help you improve? Get them involved in understanding what you're doing and why you're doing it, rather than imposing numbers that they perceive as finding excuses to give us bad raises or whatever it might turn out to be. Another classic example is you measure the effectiveness of your testing organization by how many tests they complete per week. Well, if you do that, then the people are going to create lots of very simple tests, so they'll get a big number of tests completed per week. That's not what you should be measuring. You should be measuring how effective is the testing process. And that requires thinking a lot harder about what it is you want to measure.
All right, I think we have time for one more question. Would you say that data collection that was collected by the users of your product should follow the same guidelines as data collection followed by the essentially the development team?
Well, that's actually kind of a hard question to answer because it depends on some specifics that aren't specified in the question. But what I think is that you have to measure what answers and information need. And if the different people have different information needs, then maybe you need to ask different questions and get different metrics. But it's important to make sure that they aren't contradicting. They aren't leading, you don't want the customer to get metrics that tell them that the programmers are screwed up and the programmers to get metrics that tell them that the customer is screwed up. What you want is to get something that tells you what is screwed up. And it may be that the terminology used by the customer isn't understood by the programmer, and that's neither one's fault. So the full answer to that question is you have to work together to decide who needs what information and how can we do it in a way that puts the emphasis on what are we doing right and what are we doing wrong, as opposed to blaming people.
All right, thank you very much. I'm afraid we've run out of time today. Thanks again to Dennis for his informative presentation and his insightful answers to the many questions. Special thanks to each of you for taking the time to attend and participate in today's webinar. And a reminder, this is part 2 of 4 in a series, so we hope to see you again in 2 weeks. This webinar was recorded and will be available online in a few days at www.sigsoft.org/resources/webinars.html. You can find announcements on upcoming ACM and SIGSOFT webinars and other ACM activities at learning.acm.org and www.sigsoft.org. On behalf of SIGSOFT, the speaker, and myself, thanks again for joining us, and I hope you will join us again in the future. This concludes today's webinar.